Okay. Good morning. We sit there. I'm waiting for Trần Quốc Khang. Where is Trần Quốc Khang? He's not there. Huh? And Huỳnh Ngọc Tân. Huỳnh Ngọc Tân. Still absent? Okay. So, where is Bá Thanh? Bá Thanh and Hoàng Việt. Trần Bá Thanh.
I'm here, sir.
What you have to do for? What you should do? Thanh, let me know. Thanh left the meeting. Okay. Hoàng Việt. Where is Hoàng Việt?
I'm here, sir.
Okay. What you have to do for? What you have to do?
Let's.
What you have to do for? And where is Bá Thanh? He left. Okay, Bá Thanh is left. Okay, where are you, Bá Thanh? Hoàng Việt. Okay. Problem with the electricity. Okay. Đặng Hoàng Việt.
Yes, sir.
Okay. So, can I see your whole face? Okay. So, do not let me remind that issue many times. Yeah, okay. Now we start with the chapter 6. We discuss about the Z transform and the application to the analysis of LTI system. Okay. So bear in your mind, this is the most important chapter. Okay, the most important chapter. So, take a look. Now, the chapter we discuss about the basic properties and the region of conversion, the causality and stability. Okay, this one we also link the ROC together with the causality and stability. Okay, and what about the application? Yeah, we apply the Z transform to drop or to sketch for frequency spectrum. Do you remember what the common methods we can use to sketch for the magnitude and phase of a complex function? Any of you can answer? Huh? Any of you can answer? What the common methods normally we can use to sketch for the magnitude and phase of a complex function? Now, what's the name a proper name of the mythos. I believe all of you already learned, yeah, in several courses, not only one course, but several courses. What is this? What is the name? What is the name of the common mythos we can use? Normally, we use to sketch for the magnitude and frequency, magnitude and phase response of a complex function. Of course, the function versus omega. Yeah. Think over, and any of you can answer a question. I believe you. Now, I try to review and forcing you, okay, to remember what you have learned. Okay, so very much popular methods. Yeah, we use to sketch for the magnitude and response and the phase of the complex function in general. Of course, the frequency response is also belong to the complex functions. Okay, for example, in elliptical circuits, when you work out for the transfer function and you use a Fourier transform to convert it in the frequency domain, what the common methods we use to sketch for the magnitude and phase of the function? Now, the Fourier transform just provide you the omega or f function, but what the methods we use to sketch for the magnitude and phase of that function? How can we sketch for the magnitude and phase response of the function? Hmm? How? Try to remember. The answer is the both plots. Hmm? Haven't you learned about the both plots? Hmm? How? Yeah, very much popular, not only in analog. So really, what about the what about what you call electronics circuits? I don't think so. When you learn electronics, you have to find out the transfer function, okay, the frequency response of the circuits. And after that, when you put the C and the L capacitor and inductor into the account, then the frequency response, it is a complex function. And very much common, we use both methods to sketch for the magnitude and phase of that function. not only in electronic circuits, but also maybe in automation, okay, control engineering, electrical circuits as well. When you want to sketch for the magnitude and phase response of function. How about you, with where is with?
I'm here, sir.
Haven't you ever heard about the Bose plus?
Yes, I heard it in the course analog signal.
Okay, analog signal. And did you use this one to sketch for
Uh,
the magnitude and phase?
yes,
Okay, yeah, definitely. I believe not only in this one. Yeah, I still remember sometimes in math also when you learn about the complex function. Okay, when you learn about the complex function, yeah, you may use a book plots to sketch for magnitude and response of the function as well in mathematics. Yeah. Okay. Anyway, so and the book plots sometimes is very difficult to implement the case because for the case of the book plots, we have to split the function up into a multiple product terms, and then you sketch each of them. After that, you add them up. Okay, even each is the phase or the magnitude. So that one sometimes is not so easy. Yeah, sometimes not so easy to build up the function to fractions the function like that. But this one, yeah, instead of we use a book loss, yeah, we can use the free function, free. Okay, sorry the interruption. Now this one, instead of we use a frequency, we use a book loss to sketch for magnitude and phase response. We can use the z function. Okay, we base on the z function and drop for the magnitude response. That means the function versus omega. Very much easy and comfortable when we use that one. And final one, yeah, we talk about the inverse z transform and the methods, namely partial fraction. Okay, partial fraction. Now, this one, just by definition, yeah, just by definition, like as the Fourier transform or any signal transformation, we just based on the definitions of the transformation to work out for the transformed signal. Okay, this one just the definition. Okay, the definitions of the Z transform. So I want to remind you again what the corresponding Fourier analysis when we compare it to the Z transform. Any of you can answer, yeah? What the corresponding Fourier analysis when we compare to the Z transform. I showed you already when we start the course. Okay, I figure out all of the signal transformation and what the equivalence or what the corresponding Fourier analysis compared to the Z transform. Do you remember Thanh? Thanh, bác Thanh, bác Thanh. There's a bác Thanh. Okay, yeah. Maybe bác Thanh got a problem. Bác Thanh maybe got a problem with the electricity. So, okay, Viet, do you still remember what the corresponding Fourier analysis when we compare it to the Z transform? I let you know already. You have many categories of the Fourier analysis. Yeah? Okay. What is the corresponding Fourier analysis when we compare it to the Z transform? Okay. Now, that is a problem. I think. Do you take notes when you listen to the lecture with? Hmm? With? With? Where are you?
Yes, sir. Yes, sir.
Do you take notes when you listen to the lecture?
Yes.
Yes or no?
Yes, sir.
Yes. How? How?
I take note in my book.
Nope. That is not very much convenient. Yeah. And if you take notes, now answer the questions. I did let you know already. Yeah. The equivalence of corresponding Fourier analysis when we compare it to the Z transform. How do you remember? How? What what kind of the Fourier analysis equivalent of corresponding what kind of what what kind of the Fourier?
Laplace.
No, not like that. Which is the DTFT. If you take notes well, yeah, this one is very much easy. Yeah, I still remember. I already circled. Yeah, the corresponding Fourier analysis to the Z transform. Okay, so discrete times Fourier transform. If we substitute Z by e power of j omega, then we get back the formula for DTFT and vice versa. When you know the DTFT, and then you can substitute Z by e power of j omega. Then you can work out for the formula of the sequence. Okay? So the problem now, just I just want to know Who who has a hard copies of the slides in hand? Yeah? Raise your hand, please. Click to the hands box. Let me know how many of you. Okay. And okay, no. Raise your hand in the case of you have a hard copies of slides in hand. No one? Hmm. No one. Even Tan, huh? But Tan. Monica?
Sorry, sir, I'm here. What did you say?
Okay. My
What did you
question,
say? I
yeah,
cannot hear clearly.
my question, I just want to know who has a hard copy of slides in hand?
Uh, I do not use a hard copy. I use my notebook to take notes.
No one raised a hand. So that one is not the good way to go. Yeah? Strongly recommend. My experience, my experience. When you got a hard copies of slides in hand, then you can easy to take notes. And normally through the lecture, I try to let you know the keywords of the problem of the issues. So when you have a hard copy, you can easy to take notes. And later on, or any times, yeah, you can open the hard copy, yeah, to review the lessons. I believe much more convenience compared to the computer. You want to take notes. You have to open the computer and the writing, the technology is not so much convenient when we compare to the hard copy. Okay, normally in class, I always recommend the student that it should be better because it's quite easy now, easy and very much comfortable for you to print out the hard copies of the slides. Okay, you can print 2 or even 4 slides in a piece. Okay, but very much convenient for you to take notes rather than using a notebook. Yeah. Okay, anyway, just a strongly recommendation. Okay, so that one I want to let you know. So when I check, if you take notes well, it is a quite a simple questions. Okay, and also, yeah, can be a good help for you. Okay, to review that is the things, what the DTFT and what the Z transform and what the relationship between the DTFT and the Z transform. So that one is, yeah, would make you to remember many things else. Yeah. Okay. So this one, if we substitute Z by E power of J omega, then that one is the formula of the DTFT. Yeah? Okay. And this one, okay, for example, because the Z transform we can apply to any signals. So for example, in this case, we apply to the input response and the result xz, namely the transfer function. Okay, now, again, now, how many form? Okay, this one, the given input response like this. Okay, now I try to remind you. When we look at this one, the given impulse response, what form of the impulse response, yeah, we guess in this example. How many forms we can describe a signal? Yeah, of course, impulse response is a signal, okay? So the general concept, signal, or just stick to, yeah, just stick to the impulse response, okay? How many forms we can use to describe or writing down the strength of the impulse response, so the impulse response. I let you know already, yeah? Okay, Han, you want to answer why you join and you drop out and drop in many, many times, yeah? Okay, any of you can answer. How many forms we can use to describe? No, seven. Seven is a different one, huh? Where, do you remember? I, I put on board as well, huh? Okay, Thành, no problem. What a problem. What a problem with the connection. What a problem with your connection with Hoàng Việt, Đặng Hoàng Việt.
I'm not sure. The internet is
Yeah, okay. In my side as well, huh? The internet just drop out. So, do you remember how many forms we can use to describe for impulse response?
mm,
General one, yeah, we can describe a signal, huh? But
uh,
just stick to the impulse response. How many forms? I wrote on
I think
I
it's
still
three.
remember I wrote on board, yeah, to tell you.
I
How
think
many
it's
forms?
three.
Three, yeah? What are they? Three is correct. What are
Uh,
they?
I don't know the name. It's FIR.
No. No. We have three forms. Okay. So the first one, namely the vector form. The second, closed or recursive form, depends on whether the system is finite or infinite impulse response. Okay? And the third one is the mathematics form. mathematical form. All right? 3, 4. Okay. Now, this is a vector form. Huh? This is a vector form. When we describe, that is the impulse response, like a series of samples. And then this one we say the vector form. And when we apply the Z transform, we can easy to work out for this one with the case of the causal signal. Huh? Okay. Now, about the properties like or the signal transformation, we have 3 most important properties, namely linearity, delays, and convolution properties. For the delays, when we write down is n minus d, that means in the z domain, we multiply is z by z's power of minus d. Okay, if we substitute z by e power of j omega, so we see how similar to the case of the dtft. Okay, the Fourier transform. And the convolution, not only, now bearing in mind the 3 important properties of the Z transform, also for all the signal transformation. Yeah? Okay. Now, look at this. This is important. Now, the second, 2 Fourier can be written in the closed form. Yeah? Closed form. Because this is the equal response of the FIR system or FIR tutor. So that means we try to describe the signal against the delta function. Okay, when we express the Xn equal to 2 delta n plus 3 delta n minus 1 and then so on. So that form we say the closed form for FIR system. In the case of IIR system, we get recursive form because IIR system, we already learned there is a feedback, there is some feedback terms appear in the function. Okay, so that one we say the recursive or feedback, recursive or feedback form, right? Okay, so try to remember because later on when you work with the tutorial or the exam, sometimes the question would ask you to provide, for example, writing down what is the closed form of the transfer function, or what is the mass form of the impulse response. So you have to provide the appropriate solution too. Okay? And this one, we get 2 closed form for the FIR Führer. And here, try to remember, easy one. The Z transform of the delta n equal to 1. So every delay of the delta, okay, you can get the Z power, corresponding power. Huh? Now, and when you know about that, you can easy to get through the Z transform of the case. Okay. And the second one, okay. Now, this is important, Try to take notes in this one. Using the unit step identity. So UN equals minus un minus 1 equal to delta n. This one valid for all n. Okay. Now, use the Z transform properties. Determine the Z transform of the two signals. Is n equal to un and is n equal to minus u minus n minus 1. This one, namely the anti-causal signal. Okay, now look at this. We find out the case of A. In the case of is n equal to un. So when we apply the unit step identity, we can work out for the is n equal to this one. What about the second, the case of anti-causal? Okay, you get this one, and then you find out, okay, you can find out the z equal to the same function. Okay, both cases, we get the same z function. Or we can make a conclusion for a given z function if we want to take it back the time domain. Then the solution is not unique. Not unique. Tức là không có duy nhất, lời giải nó không phải là duy nhất. Nếu mà chúng ta có một cái hàm z, cái đề bài hỏi chúng ta là tính ngược trở lại, biến đổi nó về miền thời gian, thì cái lời giải nó sẽ không duy nhất. Nó chỉ duy nhất khi nào mà nó tương ứng với lại cái miền hội tụ ROC nào đó được chỉ định nhé. Okay. So look at this one. Okay, I'd like to spend a few minutes and look at this example by yourself. Okay, and then I will raise a question to ask you for. Spend a couple minutes to recognize what the significant information this example may deliver to you. Okay, now my question. Nguyễn Kim, where's Nguyễn Kim?
I'm here, teacher.
Okay, now answer a question. Turn on the camera. And what the significant information this example may deliver to you? When you read it, okay, you find out what the significant issues or significant information you would get from this example. I try to bring you back and try to link the past to the present together.
I think
Yeah,
it's
that's
similar to Laplace transform.
No. What you understand about the Laplace transform? Now, what? What you understand about the Laplace transform?
I think abstract transform be the integral transform of continuous function.
Yeah. Oh, I remember. Laplace transform just apply to the continuous time signal. But this one just apply to the discrete time signal. Huh? Quite different. Okay. But what the significant information this example I like to put into the slide, and what the significant information I try to deliver to you.
Uh, I think it's the coefficient of the powers of Z or the convolution Abut samples.
No. Any of you can answer? How about you? Cha Quốc Khang. Where are you, Khang?
Yes, I'm here.
Turn on the camera. Now, what is your answer? What you obtain the information from this one? Okay, can you show your whole face?
Yes, I'm here.
Okay. Now, what the significant information you obtain from this? If we link to the previous chapter.
Still thinking about it.
Okay, Huỳnh Ngọc Tân. Where are you? Tân. Huỳnh Ngọc Tân. Tân.
Yes, sir.
Okay. Now, okay. What is your answer? Why you absent many times, Tân?
Yeah, sorry, I wake up early, and, so I missed the attendance, the check attendance.
Yeah. And you miss also that is the in-class tutorial as well. Huh? Okay. So what is your answer?
Yeah, I think I need some time to.
Okay.
Yeah,
Now, Vĩnh Hảo, you remember what the significant information you obtain from this one? This example. Not really, but now the answer is this is the seventh method to calculate for convolution. Okay. I did let you know altogether we have a seven algorithms or methods we can apply to calculate for convolution. We learned already six in the previous chapter. And the last one, the number seven, this is the number seven. Okay? Now, if we want to check the convolution of two signals in the time domain, then we convert them to the Z domain. And using the convolution properties of the Z transform, we can work out for the YZ. And we can take them back to the time domain. This is the results of the convolution. Okay? So now the regional conversion in Vietnamese normally we say miền hội tụ. Okay? Like I saw the signal transformation, yeah, we address to the region of conversion because that one is what makes the condition to work out for inverse. Okay, for the inverse transformation. Okay, just by definition, this one, region of conversion of Z is a subset of the complex Z plane. Bear in your mind later on when we say Z plane, or C-plex. They are the same, yeah? Because they are the complex plane. Do you still remember the complex plane? Okay, wait, I will check. Okay, this is the complex plane, yeah? There is a subset of OZ belong to C-plane, okay? Which make the function is as not be infinitive, okay? That also means this one, the function is convergence. And the reason of conversion is an important concept in many respects. This allows the unique inversion of the Z transform and provide convenient characterization of causality and stability properties of signal system. Okay, I just let you know already because in the case of causal or anti-causal, when we convert to the Z domain, we will get the same Z function. Okay, that also means for a given Z function, if we want to take the inverse Z transform, the solution is not unique. It is unique only when we specify its region of conversion. Okay, when we know its region of conversion, and then we can work out for the unique solution for inverse Z transform. Okay, so that one is very okay. Now because from now mostly we deal with the complex function or complex value. So I want to make sure, yeah, you still remember what the basic, okay, what the basic meanings of the complex function or complex value. Okay. Now, how about you, Đặng Đức Toàn? Toàn,
Yes, sir.
okay, you still remember what the complex number and complex function and the
Yes, I
complex plane?
yes I still.
Okay.
Well,
Okay. Right. Let me okay. Can you see the ball clearly?
yes, yes.
Okay. What's the value of this part and this part?
Uh, it's I think if it is show, it have to be -1, so or that is 2.
Nguyễn Ngọc Khánh, Nguyễn Ngọc Khánh.
Mm,
Yes, I'm here.
Okay. Turn on the camera. Okay. What the value of this point? No answer. Huh? Trà Quốc Khang.
Yes, I'm here.
it
Answer. Hmm? Trà Quốc Khang. What is your answer?
I don't know.
Nguyễn Đức Hiếu. Hiếu.
Yes. is very good.
Okay. Việt, Nguyễn Hoàng Việt. Việt.
Yes.
What's your answer?
Not yet, sir.
Okay. Minor sign or
Yes.
minor sign. Right? Okay. Now, just the recommendation, you should better use J, because when you use the I, sometimes, yeah, make the confusing where for your writing of. Okay, my experience, some students when they write down the function this is I. Okay, sometimes it's difficult. Oh, sorry. Okay, so it should be better writing down the J, huh? Using the J rather than the I. Very easy to recognize your meaning for the complex value. Okay, so and because from now, yeah, very much often, yeah, we use the J functions too. Now look at the case. This is a causal signal. Okay, the causal signal. We write out the 0.5 NUN. Okay, this one is the J. This is the causal signal. And when we apply the Z transform, and if we substitute it by 0.5 Z power of minus 1, then we can use the infinite geometric series like this. Okay, this one you already use this formula in the chapter 1, huh? On chapter 1. You use to calculate for the energies of the signal. So when we apply this one, and then you can work out for the results of the Z transform of the function like this. Okay. And then, yeah, with the condition, magnitude should be smaller than 1, corresponding to this one, because, yeah, we are working in the complex plane. So then the result magnitude of Z greater than 0.5 in this case, okay, because it's equal to 0.5 Z power of minus 1. So this is the meaning outside the circle of radius 0.5. Okay, outside, or later on I just say circle 0.5. Regional conversion outside the circle of radius 0.5. Okay, so understand. Okay, this one is the circle 0.5, radius 0.5, and any Z lies outside the circle 0.5 would satisfy or belongs to the regional conversion of the function. Okay, all of the Z outside the 0.5 circle satisfy the condition, that means its magnitude greater than 0.5. Okay, I like this one. Now, what about the anti-causal case? Anti-causal case, we write down minus 0.5 and u minus n minus 1 like this. And again, we apply the Z transform formula. Then, using the infinite geometric series as well, we can get this result. Okay? But is equal to 0.5 power of minus 1 G. Okay. Then we can work out for with the condition. It is 0.5. Yeah? It is a 0.5 G power of minus 1. So then we can write out, okay, this one with the conditions. Okay, from the condition, we can work out that is the regional conversion following this condition. Okay, following this condition. Then we get, this is the case of, now this one, magnitudes of 0.5 Z power of minus 1 smaller than 1. Or the magnitude of this one smaller than 0.5. 0.5, that means inside the circle, radius 0.5. Okay? Or to summarize the Z transform, yeah, we would work out for, that is the result. They have the same function, yeah? Causal or anti-causal, yeah, the result, we get the same Z function except the regional conversion. Now, the general one, this is a causal case. We get this Z function and its regional conversion outside the circle A. Okay, the circle radius magnitude. Of course, we have to take the absolute value of A. A can be minus or plus value, but we take the magnitude because specified for the radius. And also for the causal case, we get the same function except the regional conversion. So strongly recommend you should better remember the two basic functions because later on, yeah, we can use very much often and convenient to work out for the Z transform and inverse Z transform. Okay, very easy to remember. A power of n un. Okay, and then we can derive that is equal Z transform equal to 1 over 1 minus A Z power of minus 1. And later on, A is the poles of the function. Poles and zero, I think you already know that is the basic definitions of zero and poles of a function. Yeah? When we take the numerator equal to 0, we can work out for a value of 0. And when we take the denominator equal to 0, we can work out for the poles. And this is minus A power of n, u minus n minus 1. Then we can get this one, the same function, except the regional conversion. Okay, try to remember, sir. Yeah? Try to remember, sir. Okay. So can we take a short break, yeah? About 10 minutes, and then we come back to the lecture. And by the way, yeah, you can look over again, yeah, what the significant information you obtain in the Z transformation. Okay, now we take 10 minutes for a break. Huh? Okay. See you later on. Huh? Okay, we get back. Where are you, Hill? Hill?
I'm here.
Okay. So this one, I think I make some mistake there. Okay. In this slide, look at this one. Yeah, I just have a quick look. Yeah. This one actually, I missed the minus signs in here. Power of minus n. Okay, put the minus signs in here, minus n. Right? I missed the minus sign in here. Power of minus n. Yeah, inserts to that. Yeah. And this one, we left this one equal to 0.5 power of minus 1 z. That means minus 1 power of 0.5 power of minus 1. Okay? And then, yeah, you can get this one. So try to put the change. This one, this is typing. Yeah, I did not recognize, so this one. So, and this one a bit easy to recognize. Yeah, that is with the minus signs. Yeah, we missed the minus signs in here. All right. So try to put change to this one. Okay. Now, strongly recommend you should better remember this. Okay. Try to remember this one. The two formula easy to catch up or remember for this, right? Okay. Now, for example, for this one, this is the causal signal. And if you remember the formula, yeah, you can straightforward write down the z function. And this is the regional conversion because this is the causal signal. Regional conversion outside the circle 1, yeah, a equal to 1. And this is the anti-causal. Then we have the same function. But this one, yeah, the regional conversion inside the circle 1. And this one is also, we have the causal signal. But the A is equal to minus 1. Later on, minus 1 or the A is the pole of the function. Okay, is the poles of the function. Okay, this one is minus 1. Then we get this with the regional conversion outside the circle 1 because we take absolute of minus 1. And this one is the case of anti-causal. Then we get the regional conversion inside the circle 1. All right? So, any questions about? Yeah, before I like to move to the tutorial, the previous tutorial to explain to you a bit. Any questions up to now? Where's Batan? Where are you, Batan?
I'm here, sir.
Okay. Any questions?
Mm, no, sir. Maybe no, sir.
Okay. So now we open the tutorial number 4. Okay. Now, open the tutorial number 4A. We did get through this tutorial. What, Hill? You want to say something, Hill?
Sorry, sir.
No?
No.
Okay. So, did we get through this this tutorial? I did explain to you the way to go. Hill?
Yes, teacher.
Okay. Now, just have a quick look about this one. This one is no problem with the question 1.
Yes, sir. We have go on the question of this tutorial.
Okay. Yeah. And this one as well. How about? What about?
Question number 3 and 4 we have already submit for you. Yes.
Okay, submit for me. Okay, submit to me. But yeah, many of you would provide that is not the appropriate solution. So I would check it again. For example, look at the question 3. Huh? Now, question A, 3A, determine the exam. Okay, straightforward. Trần Lê Trung, what is your answer? Trung, Trần Lê Trung.
I'm here, sir.
Okay, what is your answer for exam? What is the answer for exam?
The answer.
Okay, I get another one. Việt, Đặng Hoàng Việt. Việt,
Yes, sir.
what is the answer for exam?
The answer is xn plus 2x n minus 1 plus xn minus 2.
No, that is the wrong answer. Huh? Nguyễn Bá Thành. Bá Thành. Thành.
Yes, sir.
Okay. Can you turn on the camera?
So, what did you say, sir?
The poor connection. So, okay. I get another one. Okay, Hảo, what is your answer? Not gamma. No. That one is should be delta. Not a gamma. Yeah. N minus plus delta. Okay. This one, very much easy when you remember the basic definition of the delta function of the impulse response. So you can easy to substitute y by h and is by delta n. Okay. then you can easy to write down for the exam like this. Is the stable, it is a stable system, how? Okay, because this one we do not have any recursive terms in the impulse response function. So that one should be FIR system or FIR filter. Then definitely it is stable. Okay, and easy to determine, yeah? Determine H. And remind you again, it is the same when we write out X omega or X E K omega or X K omega. Okay, they are the same, yeah? They are the same depending on the author. Some author they may use this one, the others, the others. Okay, the same meaning for. Okay, how can we determine the HE J omega or just H omega? How? How? Okay, yeah, we apply the concept of Z transform, and then we write out the X Z equal to, this is a function of Z, and just substitute the E power of J omega equal to Z. So that one we can get, that is the frequency response of the system. Okay, and then we use a trigonometric. What trigonometric identity? How about the cos? How about the cos J omega equal to? Uh, okay, or you just, okay, anyway, okay. Now the cos J omega equal to, just to remind you, cos J omega equal to, say again, E J omega minus, okay, so that one, yeah, should be plus, yeah, should be plus, should be plus, should be plus, because we have an E power of minus J omega. So that is, yeah, namely the trigonometric identity. Okay. So, and that one is question 3. How about question 4? Now, many of you would not provide, that is the appropriate solution for question 4. Okay. Now try to look at this one. Question 4. The given is 0. Then we get the y0. And now, why the response of the system to the signal is 1n? What we can do for example, your case, how? Now, how can we work out for response of the system to the signal is 1n? What is the solution?
So
That means
can I share can I share my screen? I will show my screen.
okay, yeah, that's good. Show to everyone. Yeah, good. Now this one, if you want to work out for response of the system to each one end, the first step you should better write down the relationship between each zero and each n. Sorry, each zero and each one.
The first one to find the impulse response, uh, I will find out the length of it. I will figure out the length of the x function.
Y zero, the length is no. This one, yeah, you can do so. But now, what about the relationship between each zero and each one?
What? So can you repeat again?
What the relationship between each zero and each one?
X0 and x
Hmm?
relationship between x0 and x1. Uh,
The pen is very close to a pen, so the ink is dry very quick. So, and this is two actually. Okay. Now, what the relationship? This is a show. Now, intuitively, we can easy to recognize what the is one and is zero. What the relationship between is zero and is one? Hmm? And what what the relationship between is one and is zero? Or we write down the is one versus is zero intuitively. Hmm? you see? Can you recognize? Or any of you can answer a question. Viết, Đặng Long viết. The given is 0, huh? Here we have a 0 minus 1, 1. Okay, intuitively, yeah. What is n versus is 0? I showed you already, so you can see. Yeah? You put it into 3 terms. Yeah? Okay, now, what is 1 versus is 0? Any of you can answer? How? Yeah. We can split them up into 3 terms. Okay, you see how similar of each term when we compare to each 0. Using the delay and scaling factor. What is the relationship between this and this?
It is x0 plus x0 n plus 1, sir. x0 n minus
No, just step by step.
Yes.
What is compared to is 0?
It's the delay by one. It is delay by 1.
Delay by 1? Okay. When we
Shift it to the left. To the right, sir. Sorry.
to the right hand side, right?
Yes, this is shift to the right.
When we shift it to the right hand side, we can get this one, or this one should be is 0 n minus 1. Okay? How about this?
It is shift to the right with 5. N minus 5.
N minus 5. Okay? We shift it.
You shift it.
Plus n minus 5. And what about this?
It is we scale it up by the factor of 2.
2. Okay. Now what we compare this one to this would be?
It is 2x1 2x0 n minus 3.
Minus 3. Okay. Minus the middle one, 0, shift to 3. So we have a 0 in here, so shift 1, shift 2, shift 3. Should be shift 3, yeah? Should be shift 3. Okay? Because we stick into this one. For example, this one 1, we shift 3. So this one becomes to 4. And this one 0, shift 3 becomes to be 3. This one minus 1, shift 3 becomes to be 2. Shift 3, huh? Okay. So, and similar for this one, yeah, with the center point, we have a 5. So, the start is 0 from here, shift 1, 2, 3, 4, 5. Then we get this. Similar to this one, it is a 0. If we shift right one sample, and then 0 becomes to 1. Okay. Right? And now, how can we find out the y1? What about y1? When you have this function, okay. Now you write down in the vector form. What's the vector form of h0? What's the vector form? No, let me check. No. Oh, maybe I checked something wrong scale. Yeah. Okay. So stick to the question. Yeah, I did start 0 from 1. So if we stick into the question, it should be this one should be stick to try to look at each one and again. So this one should be minus what the delay is. Should be minus not minus one, yeah? Because I did check that is a wrong scale of the each one. So this is minus 2 and this is minus 6, yeah, and this is minus 4. Huh? Okay, it's right. Now look at that. Yeah, because I shift rise one sample of the list 1n. Now stick to the question 4. We see we start from 1 with the magnitude 1, and then 2, 3, 4, 5, and 2, 7. Okay, so if we map the E0 into the S1n, then it should be E0 n minus 2, and the center is E0 n minus 6, and the right hand side term should be E2, that is the right hand side, the most right hand side should be E0 n minus 6, and the center should be 2 scale of 2, E0 n minus 4. Yeah? Okay? This one we stick to the question. Okay, we stick to the question. Now, what the vector form of E0? How? One, two, one. Okay. So we know this one. How can we look out for y1? Okay. Okay. Because the given question gives you it is a stable LTI system. So we just straightforward apply the linearity properties. Okay. Then when we get each one is a function of E0, then we can work out for the output or the response of the system to the signal is 1n by taking the linear combination. Okay? Now, how can we find out for y1n? Finally, we just give up. Now, you write down, sorry, solution 1. is the y0n vector form? Vector form of this one is -2 -1 -2. So 0, 2, 1. Okay. So we list y0 -1 -2 0 2 1, and then we write down. Okay, that is the way to go. You know the y0 in advance. Then, when you know you write down the linear combinations of the y1 versus y0, and then we got y0 n minus 2, y0 n minus 6, and 2y0 n minus 4. After that, we fill up the table and we just add them up. Okay? Do you know the way to go? It's okay, everyone?
Yes, it's okay, teacher.
Okay. For example, if you want to write down the delays of this one, we just shift right to sample. This one, we just shift right 6 sample. And this one, we multiply by 2 and then shift right 4 sample. Okay? After that, we can add them up. What is the length of the output signal? The length of the output signal of y1n should be. Okay, no, that is just stick to the easy way. What is the length of this? We have that is the output. Okay, what is the length of the impulse response should be? What the length of the impulse response should be? When we know the output, the length of the output and the length of the input, what is the length of the impulse response should be?
It should be 3 some.
3, should be 3, yeah? The length 3, so the input is the length 3, 3 plus 3 minus 1. Then, yeah, we have the length of the output 5. Okay. So, for question A, actually, we have a couple ways to go. But this one is clearly, yeah, we can arrange or we can implement the linearity properties of the system. Okay. Because the given question provides you it is a stable LTI system. So straightforward, we can use linearity properties to find out the solution. Of course, yeah, you can run another way. Okay, another way to reach to the final by work out for the impulse response first, and then when you know the impulse response, you can easy to find out the y1n. Okay, that one is still a possible solution for, but when we stick to use the linearity properties, yeah, we should better Yeah, process like this. Okay, you have a question, huh? H, what you mean? H, you mean the info response? No, normally that is for a specific system. So we have just only one info response exchange. Are you meaning about the is or the H? I would not understand what you mean. Okay, in Vietnamese, what you would okay, is not H, yeah? Is okay, is okay. Làm sao? Nó không ở điểm không có điểm chung á hả? Không có điểm chung. À, tức là nếu mà chúng ta không tìm được cái function của x1 versus x0 cái gì? That one is what you mean? Okay. Then first step you should better find out the info response exchange. Tức là cho trường hợp đó chúng ta sẽ tìm cái info response trước, xong rồi chúng ta dùng cái phép toán convolution để chúng ta work out for the y1. Ví dụ trong trường hợp này, cách nào để chúng ta tìm cái info response nhé? Đây là cái different solution nhé. Okay. Now, actually, in any way, because this is the linearity system. Okay, this is actually the linear system. So in any way, yeah, we can work out for the relationship between each one and each zero. But depending on the vector of each one and each zero. Sometimes it's very take a long way or take a long time to work out for the relationship between each one and each zero. Okay? Or in this case, very short to work out for. But in any way, yeah, we can get the relationship between each one and each zero. Even can be difficult, complicated, or simple. Okay? But anyway, in such case, now I show you the way you can work out for the info response directly based on the zero and y0. So you know the length of this one is 5. You know the length of input is 3. Then very easy. Yeah, we can write out the general form of exchange. Okay? So, and then you check the convolution of E0 and HN. How? How can we find out for Y0 to this? By what? By what methods? Yeah, we can use to find out this.
I think we use a convolution table, and then we will get the system of equation, and then we will find out x0, x1, x2.
Okay, that's right. you can use a convolution table to generate the convolution table like this. And after that, you can easy to map this one to the y0. For example, the value of f0 equal to -1. Yeah? And you show the system equation. Finally, you can easy to work out for h1 and h2. Right? And once you know the h1 and h2, you can take the convolution of hn and h1. The vector h1, okay, convolves to the hn. Then you can work out for the y1n. Of course, the results come out similar to the previous methods we used for. All right? Any questions? You got the tutorial number 6 already, yeah? Han?
Yes, sir.
Okay. You got the tutorial number 6 already? I already upload to the e-learning.
Yeah.
Have you got it? Have you got it? No?
What? Which one? Which one, sir?
Tutorial number 6.
Tutorial number 6.
Yeah.
Let
You got it?
me check.
You got it?
I have already seen it, and I saw it. I found it in BK's learning.
Okay. My question, just you got it. You got the tutorial number 6.
Yes, I got it.
Okay. Just asking.
Yeah.
Okay. Any more questions you want to ask for? No. Try to read through the chapter 6, the Z transform. This is the most important chapter. Okay. Because later on, most of the tutorial we deal with the Z function. Any question? Kim? Kim? Khang?
Yes.
Okay. What questions?
No, I don't have any question.
Okay. No questions. Okay. Tan? Any
I'm
questions?
okay, sir.
Okay. Okay. Try your best, yeah, to read and work out the tutorial number 6 by yourself before. Yeah. I would come back and explain to you about that one. Okay? If you do not have any question, okay. Bye-bye. See you.
Goodbye.
Bye, sir.
Bye, sir.
See you.
Okay.
See you.